In the last lecture, we have seen the existence and uniqueness theorem of strong solution of a given stochastic differential equation under some conditions on the drift and the volatility parameter. So, here in that proof we have showed that given these 1, 2, 3 conditions, the first condition, let us recall, this is nothing but the at most linear growth condition. Second condition is Lipschitz continuity condition on second variable of the parameters. So, here this is drift parameter, this is diffusion parameter, and then the third condition is saying that z, the initial point, is independent to the Brownian motion. So, given all these conditions, we have asserted, or this theorem asserts, that the solution exists to the equation. So, in this sense, strong solution, that there is a solution of this equation. So, x is unknown, is an integral equation actually, but we call stochastic differential equation. This is actually stochastic integral equation. Okay. So, this is the statement what we have seen in the last lecture, and also for the proof what we have obtained is the existence of SD such that this third property is true. Okay, this fourth property is true, that this solves. Okay, x is continuous and this solves. Okay, you remember that there we have denoted x by x tilde. Okay, however, some more things to say about the solution, that x is also adapted to the filtration this. Okay, what does it mean? That x subscript t, that means at the tth time x, that we call the x t, that is the random variable, that random variable is measurable with respect to the sigma algebra, this sigma algebra. Okay, for each and every t, that we have not shown, and then this is of course obvious from the proof as we have done in the last lecture. Okay, so we are going to see today this thing. Okay, since we have already established that the equation has a solution which is having continuous path with probability 1, and that solves the equation almost surely. So, we can use those property to derive this one. So, thus for every fixed capital T positive, we have obtained a unique x tilde t, as I was telling that we have denoted x tilde. There of course, we have not denoted a superscript this in the parenthesis capital T, but here we are doing. Why are we doing? To emphasize that x tilde is obtained by fixing one terminal time capital T. Okay, just to retain the dependency of this thing on T, we are writing this way. Okay. However, this dependency is very trivial manner. So, we are going to see that in the next bullet. So, which solves the SD for all small t belongs to 0 to capital T almost surely, that we have already seen. Now, we consider another t prime which is less than capital T. Okay. So, for this t prime, now consider this process. So, this is a process from 0 to capital T, correct, x tilde t. Okay. So, this process, if it restrict to 0 to capital T prime, which is smaller than capital T. Okay. So, this process restrict to this, what do I get? Because this is obtained as solution of an integral equation. So, there on the top you have 0 to t, and small t you replace by capital T to get the full thing, but instead of capital T you write down capital T prime. So, that means you just consider only the domain 0 to t prime capital. Okay. So, the Brownian motion also you consider only 0 to t prime, everything there. So, if you do that restriction, that is same as if you have started only by considering 0 to t prime only. Okay. So, getting this first and then restricting 0 to t prime. So, this process is same as just the process what you obtain by solving the SD between the interval 0 to t prime. Okay. So, this is true, that we understand easily, because that is the very definition here. for this thing. Okay. So, I am talking about this equation, correct. In this you just write down. So, this is true for all t. So, you write down not capital T, but t prime. So, there that probability would also be 1, correct, because for all small t between 0 to capital T, this is true. So, this is true also 0 to capital T prime. Okay. So, that much only I am talking here. Okay. Now, here where we have obtained this thing, now we consider this particular process which is defined from 0 to capital T prime. So, this process evaluated at any given point t, okay, we would like to ask about its measurability, whether that process is measurable with respect to the sigma algebra. Which sigma algebra? So, here we see that, okay, this we have obtained as measurable with respect to product sigma algebra, because this is a function of t and omega. On small t you have the Borel sigma algebra, on the closed interval 0 to t capital T prime, on omega you have the sigma algebra f t prime. So, since this is a function of two variables and is a measurable function of two variables, so these functions, okay, we would get that at t prime, if you take t prime section, okay, that is also measurable. I mean, in general it is not true, but here we are going to get it is measurable with respect to the sigma algebra f t prime, as this process is continuous, okay, as this has continuous path and is measurable with respect to the product sigma algebra, this thing. Okay. So, this part let me elaborate in the following 3 bullets, because in general I cannot assure that at t prime, okay, is t prime section. So, I just know that this is measurable with respect to this product sigma algebra. From there, how can I assure that its value at t prime is measurable with respect to this f t prime? We do it in the following manner, that x tilde t prime at evaluated small t is f t prime measurable, okay, for almost every t in 0 to t prime, that we obtain from the argument of Fubini's theorem. There we do these things, okay, that we get this, you know, a particular section of the measurable function is measurable almost every t. Okay. So, that we obtain. Now, since this is true for almost every t, now we take a particular neighborhood of t prime on the left hand side. So, that neighborhood would of course have a non-empty intersection of the complement of the zero measure set where this is not f t prime measurable, or in other words we would be able to get a sequence of t n, okay, which is in the complement of the zero measure set, okay, the zero measure set where this may not be f t prime measurable. So, this t n is a sequence which is increasing to t prime, and at this t n, okay, I can always find out this sequence of t n such that at this t n if I evaluate, so this as a function of omega is measurable with respect to f t prime. Okay. So, this is true for each n. Now, we know that x tilde as a function of this small t is continuous. So, since it is continuous, as t n goes to t prime, x tilde t prime of at t n converges to x tilde t prime of t prime. Okay. So, since t n converges to t prime and x tilde is continuous with probability 1. So, this we are going to get this converges to this almost surely. Okay. Now, this is a sequence of measurable functions that converges almost surely. So, the limit is also measurable with respect to the same sigma algebra. So, these are measurable to f t prime sigma algebra. So, this limit x tilde t prime at t prime is also f t prime measurable. So, that is the thing asserted here. Okay. So, these 3 bullets, okay, explain this claim. Okay. Now, we go back to this scenario that, okay, so x tilde capital T, okay, at 0 t prime, this restriction is same as this measurable function, and from this we have obtained that t prime value is measurable with f t prime. What does it mean? It means that this function's value at t prime is also f measurable with the f t prime. But what is the value of this function at t prime? That is nothing but x tilde t at t prime, because this is the just the restriction, but at t prime its value is x of t t prime. Okay. So, what we have obtained is the following, that x tilde t at t prime is measurable with respect to the sigma algebra f t prime. But what is t prime? For every t prime less than capital T. Okay. So, this is saying the same thing, that x tilde is adapted to the filtration f t small t belongs to 0 to capital T. Okay. For every time small t, the process is adapted to the x tilde t small t is measurable with respect to f t, or in other words the full process is adapted to the filtration f t. Okay.